Okay, so we have seen the select algorithm and randomized select algorithm, where basically the problem is to find the ith smallest element. Now, we have seen that depending on the, because basically we are using the quicksort partition algorithm. So, basically depending on the partition, the pivot element, we have the it partition the array into two parts. So, depending on this, it will give us the time complexity, but in the worst case always it is 0 is to n minus 1 in the worst case. So far we have seen. Okay, so now we in this lecture we want to talk about a guaranteed, I mean worst case linear time time complexity for finding the ith smallest element, and this is guaranteed worst case. So this was invented by these people, Bloom, Pratt, I think Rivest, 4 scientists and Tarjan. So in the work they have, so that was in I think 1973. So this algorithm is proposed by this 4 scientists in 1997. So idea is to basically, their idea is to generate a good pivot. So idea is to generate a good pivot recursively. So what do you mean by good pivot? Good pivot. So bad pivot means it is always minimum or maximum. So that means it will be always partition always 0 is to n minus 1. Now good pivot means if we can ensure that some portion of the element will be less than x, some portion of the element will be greater than x. Maybe it is very little portion, 1 by 10 is to 9 by 10. Then also we have seen we are lucky. Then also we have seen we have linear time. So if we can ensure, the pivot is good in the sense that if we can ensure there are certain portion, maybe very small amount, even it could be work for 99 by 100. So if we can ensure that a certain portion is less than x and certain portion is greater than x, then that choice of pivot is good pivot. So the idea is to get such a pivot. If we can get such a pivot from this array, so we will use that pivot and then we call the partition. And then obviously if we know that there are some portion guaranteed, there are some portion will be left side and some portion will be right side. If this thing is guaranteed, then if we call the partition, then obviously it will be array will be like this. So it is guaranteed that some portion will be here, some portion will be here. So that means when we call the again the recursive call, this then we will go for here again in this subsequent recursively we are calling this divide and conquer technique. Even in this call, even if we can choose again a good pivot for this this sub call, then also again it will partition into certain portion over here. So not, so we want to avoid the 0 is to n minus 1 case, and that can be avoided only by choosing a good pivot. That will guarantee that there are some portion over left side, some element less than x and some element greater than x. So the idea is to choose how one can choose a good pivot. So that is their idea. So if we can choose a good pivot which ensure that, and that choice has to be recursively, that ensure that that guaranteed there will be some elements which are less than x, there will be few elements which are greater than x. Then we choose that x as our pivot and then we call partition, and then that will be that partition will be divide the array into like this portion, not that 0 is to n minus 1. Okay, so how one can choose a good pivot? So for that, what they did, so we have given an array. So what we are doing? We are dividing this array into 5 element groups. So we have given the array of n elements. So we are dividing into 5 element groups like this. Okay. So, we are grouping the elements into 5 element groups like this. Maybe in the last one we have only 3-4 element, because this n may not be multiple of 5. Okay, but anyway, so this is our, we have given a array, A is from, say we have A array, say 1 to n or p to q. So, we take first 5 up to 5 as a first group, second group, like this. So, we are grouping this array. So, we divide the array into 5 element groups. Okay. Now what we are doing? Now we are finding the median of this group. So, this is only 5 elements. So, we can sort it off. We can just sort the element and we can get the median. Suppose this is the median of this group. Okay. And this is the median, this is the median, this is the median, this is the median. So, we sort this and got the middle point of the group. So, these are the medians of this individual group. Okay. Now, we find, so we have how many groups are there? So, there are n elements. So, roughly n by 5 groups are there. So, that means n by 5 medians are there. Okay. So, among these, so now we have n by 5 medians. Now, we find the medians of the medians, and that we will find recursively by the same function call. We will come to the code. So, now we want to find the medians of medians. So, suppose this is the medians of median and this is the medians of median, and this we are going to choose as a our x. So, this is basically our pivot element we are going to choose. This is our x. Okay. Now, if we can choose this as a pivot, then why it is a good pivot? So, that means what is the guarantee? So, good pivot means it will guarantee that some fraction of the element will be less than x, some fraction will of some portion of the element, some portion will be greater than x. So, this we have to argue. So, this is the medians of medians. So, now we will follow this notation. So, this is median of this. So, this is less than this, this is less than this. So, we will use this symbol as less than. So, this means this is lesser, okay, and this is bigger. We can use this symbol lesser by this. Okay, so, this is the medians of medians. So, this is lesser. Now, this is lesser than this, like this, like this. Okay. Okay. Now, this is the median of this group. So, that means this will be lesser than this will be lesser than this, and this is like this. So, this is lesser, this is lesser. So, like this we have. So, this is the median of this group. So, this is the relation we have, less than relation. So, this is the median of this group. So, this is lesser, like this. So, we continue with this, like this, like this, like this. Okay. So, you can leave the last one like this. Okay. So, now, if we look at all the elements over here, say this element. Now, this element is less than this, because this is the median of this group. This element is less than this. Now, this is the median of, then now this element is less than this. So, that means this element is less than this. So, if you take any element over here, they are basically less than equal to x. So, all the elements over here are basically less than equal to x, and that is guaranteed. Okay. Because if you take any element, this element is less than this is the median of that group, and this element is less than this, because this is the median of the medians. So, that means this element is less than this. So, this is true for any element less than equal to. So, if you take this element, this is the median of this group. So, this element has to be less than this. Okay. So, So, this is the less than symbol we have used. So, this is the portion where all the elements are less than equal to x, and similarly this is the portion so this is the portion if you take this element, say this element is greater than this and this is greater than this. So, this element is greater than this. So, this is the portion where all the elements are greater than equal to x, okay. Because by this relation if you take this element is less than from this group median and this median is less than from the medians of the medians. So, this element is less than this. So, we have a portion guaranteed, we have a portion which is less than x, we have a portion which is greater than x. Now, what is the size of this portion? Now, size of this portion is basically so there are n by 10 medians, n by 10 groups. Now, this is almost half of there. So, size of this is basically n by 5, size of this is n by 10. So, among this n by 10 there are 3 elements from each group. So, there are n by 10 such groups are there which are basically the above portion of which is basically less than x. And how many of them? 3 of them. So, basically 3 n by 10 is the size of this 3 n by 10 is the size of this portion where elements from that group, that portion is less than equal to x. And similarly, here also the size of this portion is 3 n by 10. So, basically x will be sitting somewhere here. So, this is the this is 3 n by 10 and this is also 3 n by 10, and if we x will be somewhere in this here, we do not know where will be x, but this is guaranteed. So, this is the good pivot, because we are guaranteeing that there will be some portion which are less than x, 3 n by 10, that portion size is 3 n by 10, and there will be some portion which is greater than x, 3 n by 10, and x will be sitting somewhere here. Okay. So, now if we take that x as a pivot and then if we call the partition, then it will be like this. So, x will be sitting somewhere here and this. So, this is the guaranteed that the partition won't be 0 is to n minus 1. So, we are ensuring that there will be some portion which is less than x, there will be some portion which is greater than x. So, that if we can ensure, then if we call the partition algorithm by choosing that x, then it will not give us the worst case scenario like 0 is to n minus 1. So, it will give us some fraction left side, some fraction right side. So, that will give us the recurrence. So, we will talk about that, but this is the idea. So, this is the idea to choose a good pivot. So, this way we choose the good pivot, and so here also we are involving some time. So, this should be taking considered into the algorithm. So, that we will write the pseudocode for this, but let us just recap this. So, this is what we are doing. We have a n element, we are partitioning, we are dividing the element into 5 element groups, and then we choose the median of each groups. Maybe there are 5 elements, so we can just simply sort this and we can find the median, and then we find the medians of the medians. Okay. So, we will write the pseudocode for this, and then that we are going to choose as a pivot element, and then we call the partition by taking this x as a pivot, and then this will partition into it will avoid the worst case scenario, and then we have the same select. So, we will find the rank of this, and then if the k is less, then let us write the code. So, this is the idea behind to choose a good pivot recursively. So, So, let us write the pseudo code for this algorithm. So, this algorithm we refer as, say, this is also select, but capital select, say. So, we have n elements, say 1 to n. So, what we are doing, let us write this in English description. So, we divide the array, divide the n element into group of 5 element, groups of 5, and then we find the median, of each group, of each 5 element group. Okay. Then, so we got the median of the each group, then we find the medians of the medians by using the same select algorithm. So, that is the recursive call. So, use the same select to find the medians. So, we have how many medians? So, we have n by 5 groups. So, now we have n by 5 medians. So, now we want to find the medians of medians. So, we call the same select to find that. So, we recursively call the select, same function, to find the median, and that is our pivot x of the n by 5 group of median. So, we have medians of medians. I mean, here we can use the lower ceiling because n may not be a multiple of 5, median to be the pivot. So, x is this medians of medians is our pivot, and that we are finding using the recursive call of this same select function. Okay, so we will talk about time complexity. So, now this is our pivot element x. Now, we use this pivot and then we call the partition algorithm, and so we partition the array around the pivot. We partition around the pivot x, and then let k be the rank of x. Okay, so if we call the partition, it will return the position. So, suppose it is we call the partition. So, suppose this is 1 to n, but in general it is p to q. So, it will return the position of x, and then r minus p plus 1 is basically our k. So, k is the this is the array thing. This is the index of the pivot element. So, r minus p plus 1 is basically this is the rank of x, where x is sitting in the sorted array. Okay. So, now, so this is the r will be the r is coming from this partition algorithm, and now, so we know the rank of x. Now, the code is same. If I is equal to k, then we are lucky, we return x because we got the ith smallest element. Otherwise, if I is less than x, then we have to call the select again. So, that means r is less than x means we have to look at the, so it is dividing array into 2 parts. We have to look at the left part of the array. So, a recursively call select from a. So, if it is p to q, so here it is say p to q, and if the partition is returning r, so this is basically p to r minus 1 comma I, else if I is greater than k, then we call the select. So, we have to look at the right part of the array. So, this portion of the code is similar to the select algorithm. So, only thing here difference is the choice of this pivot element. Okay, so this is the, so this portion is similar, but only thing this is the way we choose a good pivot. So, that is the idea. So, we have to choose a good pivot in order to avoid the that partition 0 is to n minus 1. So, this is the way we choose the good pivot. So, let us write the time complexity of this. So, how much time we are spending here? Okay, so, for that let us just write the Tn be the time complexity for this runtime. So, we divide the element into 5 element groups and find the median. So, how much time we are spending there? So, basically so we have n elements. So, we are dividing into 5 element groups. Sorry. So, how many groups? So, n by 5, and each group we are finding the median. So, we can just sort these 5 elements excuse me. So, only 5 elements. So, this will take constant time. So, there are n by 5 such groups. So, this is a theta of n. Okay. So, now recursively we call. So, now we need to find the medians of this median of the median. So, that for that we are again calling the same select. So, that will take us theta of n by 5, t of n by 5, because we are calling the same function recursively, t of n by 5. Okay, so then this step will take the partition will take the linear time theta of n. Now, if you are lucky enough, we will got this as x, but otherwise we have to go for either left part of the array or right part of the array. This is the conquer step. So, we have to call either left part of the array, right part of the array. So, for that, what is the size of that? Maximum size. Maximum size is basically, so it is basically dividing the array into 2 parts. We know that this part is 3n by 10, and in the worst case, suppose x is sitting here and we are going to call the right part of the array. So, this is roughly 7n by 10. So, this is basically in the worst case, this is basically t of 7n by 10, okay, because in the worst case we have to go to the right part, which is the biggest one. This is the worst case analysis. So, the Tn is basically sum of this. So, Tn is basically, so T n by 5 plus T 7 n by 10 plus this theta of n, theta of 1, theta of n, all combined. So, this is the recurrence we got for this select algorithm. Okay. So, now we have to get the time complexity for this. We need to solve this. So, how to solve this? So, we can try for recursive tree to get the solution. Otherwise, we can try for substitution method to get the solution. So, let us try for substitution method. So, we are thinking that Tn will be big O of n. Okay, so this is our assumption. So, that means we are thinking that Tn must be less than equal to some Cn, some C constant. So, now we need to take a substitution method. So, we need to take a induction hypothesis. So, we assume T of k must be less than C of k for all k less than n, and then we need to prove that T of n is less than this. Now, we have this recurrence. Now, this is basically less than. So, this is n by 5, which is less than n. So, we use this induction hypothesis. This is C n by 5 plus we have again 7 n by 10, which is also less than C n by which is also less than n. So, you have this in by inertial hypothesis we can just write C7 n by 10 plus theta of n. So, this is basically what? This is basically 10 into, so Cn we take common. So, this is 2 plus 7 plus theta of n. So, this is basically what? So, 9 Cn by 10 plus theta of n. So, this is basically we can write this at. So, we want to write this, we want to show this less than Cn. So, to show this we have to write this to be Cn minus of some quantity, and that quantity has to be positive. So, what is that quantity? So, basically Cn by 10 minus theta of n. So, now this so we choose C in such a way that this will be positive. So, C is in our hand. So, we can choose C such a way this will be positive, and then if once this is positive, this can be written as C of n. So, that means this is established. So, by the help of so this is the substitution method. So, we can just write C of n is T of n is less than C of n. So, this imply by the substitution method theta of n. Okay. So, that is the worst case runtime for our select algorithm, and this is not a randomized algorithm. This is just a this is to get the pivot as a good pivot. We choose the pivot, good pivot in that way. So, this is the guaranteed. So, guaranteed worst case runtime is linear by choosing that. Even we can establish this by using the recursive tree. So, one can draw the recursive tree and can see that the runtime will be also linear. So, this is the worst case linear time order statistics finding the ith smallest element, and this is the guarantee. This is not the expected, this is not the average case, this is the worst case linear time algorithm for finding the ith smallest element. Thank you.